Hi everyone. I just wanted to make this video to clarify a few things for the class. These were a lot of things that I saw people asking about, and I just wanted to go ahead and sort of clear up a few things. So first off, let's talk about formal charge. I'm going to put FC. To find the formal charge, all you have to do is count the number of valence electrons an atom usually has. So for example, for fluorine, that would be 7. For oxygen, that would be 6. Nitrogen, that would be 5. And carbon, that would be 4. And you can sort of figure out how many valence electrons an atom is supposed to have by looking at the periodic table. So let's say the periodic table looks something like this. And so, of course, over here are the noble gases. And they are going to have 8 valence electrons. Their octet is going to be full. They're going to be non-reactive, inert. So we can see here, here's fluorine, here's oxygen, here's nitrogen, here's carbon. So if you start with 8 electrons at noble gases, every time you move a space this way, you're going to go down by 1. So fluorine has 7, oxygen has 6, nitrogen has 5, and carbon has 4. So that's sort of how you tell how many valence electrons an atom has. So you start with the number of valence electrons an atom usually has, subtract the number of bonds that the atom is attached to. So let's say we have a carbon with a double bond right here, a bond right here, and then a lone pair right here. This carbon would have 3 bonds. And then we subtract the number of electrons in lone pairs. So this is the total number of electrons, not the number of lone pairs, rather. So you can see here, there are 2 electrons in lone pairs. So if I were to find the formal charge for this guy here, I would say 4 being the number of valence electrons that carbon usually has, minus 3 bonds, minus 2 electrons in lone pairs. As a result, this carbon would have a formal charge of -1. Okay, so that's how you find the formal charge. So next, I sort of want to go over hybridization. So in organic chemistry, we are usually going to be talking about 4 hybridizations: 1s, sp, sp2, and sp3. 1s is generally reserved for hydrogen. Hydrogen will 99.5% of the time have the 1s orbital, and that is because it can only hold 2 electrons, and the 1s orbital holds 2 electrons. So the hydrogen will always be using that 1s orbital. The sp, sp2, and sp3 orbitals, however, are a little bit more complicated. This we will use with atoms other than hydrogen, usually oxygen, nitrogen, and carbon. So the way that we figure out which hybridization an atom has, we have to go by how many electron groups it has. And side note, this hybridization has a lot of explanation behind it, but I'm just teaching you sort of how to solve it and how to understand it. So like if I were to ask you, what is the hybridization of this atom? This is how you would solve it. If you want to learn more about the ideas behind it, the theories behind it and everything, just go and look up a video on that. And also your professor should explain it in class. So back to this. So sp, sp2, sp3 all has to do with how many electron groups are around said atom. So let's look here really quickly. So sp, we have 1s and 1p. 1 plus 1 equals 2. I'm getting somewhere with this, just bear with me. sp2, 1s, 2p, 1 plus 2 is 3, sp3, 1s, 3p, 1 plus 3 is 4. So 2, 3, and 4, this has to do with the number of electron groups around an atom. So if your atom has 2 electron groups around it, it will be sp. If it has 3, it will be sp2. And if it has 4, then it will be sp3. So what is an electron group? Well, generally an electron group will either be a lone pair, a single bond, a double bond, or a triple bond. Even though the bonds are made up of different amounts of electrons, each one will count as 1 electron group. So each one of these, a single electron group. So for example, let's take that carbon from before. So we have a double bond here, a single bond here, and a lone pair right here. Of course, we already said the formal charge is going to be -1. So now let's look at this carbon. How many electron groups does it have? It has one in the form of the double bond, one in the form of the single bond, and one in the form of the electron pair. Every single electron pair around an atom will count as its own individual electron group. So in this case, this guy has 3 electron groups, and as a result, we would consider it sp2. So what do we do with these sp, sp2, and sp3? Well, sp, sp2, and sp3 tell us the molecular geometry of these different atoms. So I'm going to go ahead and clear my drawings. So again, we said we have 2 electron groups, that'll be sp, 3 electron groups, sp2, and 4 electron groups, that would be sp3. Now, if you recall from your Gen Chem class, whenever you have electron groups around an atom, they are going to want to maximize the angle between them. So let's take sp for an example. So here's our atom and has an electron group on this side and an electron group on this side. Obviously, to stay as far apart from each other as possible, they're going to create an angle of 180 degrees. As a result, the molecular geometry is going to be linear because a line has an angle of 180 degrees. If you haven't taken geometry in a while, that's fine. You don't have to really know this 100%. Just know that if you see sp, you're going to be linear, and the angle between the 2 electron groups is going to be about 180 degrees. Let me move this down very quickly. And so the same idea can be applied to sp2 and sp3. So let's say we have our atom right here, we have an electron group right here, and one right here. Obviously, to stay as far apart from each other as possible, they're going to make this triangle right here. And each angle is going to be about 120 degrees because that's the angles between 2 points in a triangle. So then we see, okay, these are 120 degrees. What do we call this molecular geometry? Well, we call it trigonal planar. Obviously, it's trigonal because it is a triangle, and planar is because these are all in the same plane, so we can draw it flat. Now, sp3 gets a little more confusing. This is where we're going to be using solid wedges and dashed wedges. Remember, a dashed wedge is going into the page away from you, and a solid wedge is coming out of the page towards you. So if we have an electron group here, 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 and here, they're going to make a geometry known as a tetrahedral. The way that I always remembered this is tetra means 4. If we have 4 electron groups, it's going to be tetrahedral. And this is generally how you would draw that structure here. If I were to draw this in like an artist, it would look kind of like this, I suppose. Okay, so that's what these different hybridizations and what they correspond with. Oh, and tetrahedral, it's going to have about an angle of 109.5 between each electron group. This one is probably the hardest one to remember versus the trigonal planar and the linear. So let's go on to how do we denote these different, these hybridizations in a problem? Well, before we do that, I'm just going to go ahead and draw a random linear structure here. So let's say that we have this guy right here. So I drew this in linear format. What you guys are probably used to is Lewis structure format. And I'm going to go off on a tangent here just explaining linear format. You can skip through this if you already understand it, but I'm just going to sort of explain this really quickly. So each point on the line, or each corner on the line, is going to represent 1 carbon. And also, if we have, let's say we have a triple bond right here, each end of the triple bond will be 1 carbon. The reason why we draw the triple bond as a straight line instead of sort of angled like the other ones, it has to do with that molecular geometry. The carbons will be sp hybridized, thus they'll be linear, so we draw it straight. So each one of these pink dots that I've drawn represent 1 carbon. And each of those carbons has a filled octet. And unless there's a charge, a formal charge on the carbon, we assume that the octet or the remaining bonds of the octet will be filled by hydrogens. So for example, if we look at this carbon right here, we can see it has 1 carbon-carbon bond. To fill the rest of its octet, it has to have 3 other bonds Those 3 other bonds will be to hydrogen. Now let's look at this one right here for another example. This guy has 3 bonds, 2 as a double bond, and then 1 as a single bond. So it has 3 bonds. To fill that last bond, it's simply going to make a hydrogen bond right here. So that's sort of how you tell what a line angle structure is. It's just because organic chemists are lazy and they don't want to draw every single hydrogen. You'll thank them in the future, I'm sure. But anyways, so let's get back to this. I'm going to erase these hydrogens. I'm going to keep that blue hydrogen for a second. So we are going to say what orbitals make up this bond right here. So remember what I said, hydrogen will always be 1s. So we know that one side of the bond will be hydrogen 1s. I put the atom and then the actual orbital that its electrons occupy as a subscript. And then we see here, oh, there's this carbon. It has 1, 2, 3 electron groups. So it's going to be a hydrogen 1s connected to a carbon sp2. Okay, and so then that's how you sort of write out these answers. All right. So next, this will be probably the last topic that I really cover today. I kind of want to again go over line angle structures versus a condensed structure versus all the other, versus the Lewis structure. And I'll also, I lied, this will not be the last topic. I'm also going to go over stuff like constitutional isomers versus resonance structures. You probably haven't seen resonance yet, that's fine. I'm going to go over it today. So first, let's talk about line angle structure versus Lewis structure versus condensed formula. So Lewis structure is probably what you're used to. So let's say we have a carbon right here for 3 hydrogens around it. It's attached to another carbon, which is double bonded to an oxygen, which is then bonded to an OH right here. So this is a Lewis structure. Let me draw on the electrons here. This is what you're sort of used to. What we use in organic chemistry is either going to be the condensed structure or it's going to be the line angle structure. Most of the time we'll use a line angle structure, but you need to know how to read that condensed structure. So basically that condensed structure is going to just be the atoms that are a part of our total Lewis structure. And we do this in sort of parts. We break them up into chunks. So let's break this guy up into 2 big chunks. So we have 1 there and then 1 right here. That first chunk, that's going to be CH3. This second chunk, it's going to be C, oxygen, oxygen, hydrogen. And we can see here that carbon is bonded to both of these oxygens, and then this last oxygen is bonded to this hydrogen. So this is the condensed formula. If I were to write this out, I would say, okay, so if I didn't know this was here, I would say, okay, I know I'm going to start with a CH3. And I know that CH3 is going to be attached to another carbon, and that carbon is attached to 2 other oxygens. For a carbon to be attached to 2 other oxygens, it has to be double bonded to 1 oxygen and single bonded to another oxygen. That leaves only the hydrogen left to bind to that oxygen. Okay? And so then this is how you go between these 2. So now the line angle structure. I've already sort of expressed how to sort of read a line angle structure. So I say, okay, I have 1 carbon, I have 2 carbons. This is going to be my carbon chain, quote unquote. There's only 2 carbons here, but let's say it's a chain. And I say, okay, so this carbon here, this pink carbon, is going to be this carbon here. And so what this means is that, okay, this carbon is going to be double bonded to an oxygen, and it's also going to be single bonded to an OH group. And so then here is our line angle structure. Basically, again, you do not draw on the hydrogens, but you do draw on the other heteroatoms. And also, one thing to note, I did draw on the hydrogen here. That is because you only don't draw on hydrogens when they're attached to a carbon, okay? And so that's the general rule about going between them. So let's say that we have a condensed structure and we don't have the actual Lewis structure. So I'm just going to make this up really quickly. I'm going to cross my fingers that it actually works. So I'm going to say CH, CH2, OH. So I say, okay, I'm going to highlight this into sections. So here's section 1, here's section 2, here's section 3, here's section 4. If I can change colors, there we go. So section 1, I'm going to draw in pink. So I see here, okay, so I have a CH3, 3, 2. That means that these two CH3s are going to be equivalent, which means they're going to be attached to the same atom. So I'm going to say, okay, there's one CH3 here, there's one CH3 here. I'm not drawing the line angle or the Lewis structure. I'm sort of drawing a bastardized version of both of them together. I just want to show you where I'm getting this line angle structure before I actually draw out the full thing. And so then these two, they're going to be attached to the same atom. What is that atom? Well, the only one that it's next to in the condensed formula is this CH. So here's our CH. Oh, sorry, that should be just a CH. And so we say, okay, so this CH has 3 bonds. It needs 1 more to complete its octet. You can see here the only other atom, or the only other group of atoms it's next to is this CH2. So then it's connected to this CH2. And then we say again, okay, this CH2 has 3 bonds. It needs 1 more to fill its octet. We can see, oh, it's right next to the OH, so it's attached to the OH right here. And so if I were to draw this as the line angle structure, I would make dots just so I know where my carbons are. And then I would just link them together like this. Here's the OH. And notice here how I drew them in the zigzag pattern. When you do line angle structures, you're generally going to draw them in the zigzag pattern, except if it's a triple bond. If it's in a triple bond, then we draw it linear to reflect its molecular geometry. Okay, so now I just want to quickly cover something called resonance structures. It's probably been like a billion years since you took your last chem class, so I'm just going to start from the basics. So let's say that I have a carbon that is double bonded to an oxygen here, and it has a negatively charged oxygen right here. And then it's attached to something else, I don't know, hydrogen. Okay, so let's look at this guy right here. So I say, okay, this oxygen has a negative charge, and it also has a bunch of extra electrons. This oxygen here, neutrally charged, it has a double bond. And I say to myself, do I think that I can move the negative charge off this oxygen somehow by moving these bonds around? So what I do is I say, okay, if I want to make that oxygen neutrally charged, again, I'm going to think about, okay, what would be the formal charge neutral be? That would be 6 being the number of valence electrons that oxygen usually has, minus 2 bonds, minus 4 electrons in lone pairs equals 0. And this is sort of easy to see because we have a really good example right here. Okay, so I say, okay, what if I convert one of these lone pairs into a new double bond? And so the way that I would express that is I would draw an arrow going from those electrons to this middle bond right here. And then I say, this carbon cannot have more than 8 electrons. So we have to break a bond somewhere. And the bond that we usually are going to break is going to be a pi bond. Luckily, we have one of those right here, breaks to go on the oxygen, and then we end up with our resonance structure. So in essence, a resonance structure, or the resonance structures, are going to be the alternative forms of a particular molecule, a particular molecular compound that only changes where the electrons are. It only changes where the pi bonds are and where the lone pairs are. It does not change the actual connections in a molecule. If we change the actual connections in a molecule, we would end up with something called a constitutional isomer. So let's say that we want to draw a constitutional isomer of this. So that would be if I said, okay, so what if I move this hydrogen atom off of the carbon somewhere else? The carbon would be double bonded here, it would be single bonded here, and I say, okay, I'm going to move my hydrogen right here. And so now the carbon has its lone pair, the oxygen will have its lone pair, and then I put the negative charge now on the carbon. Notice how all of these have the same overall charge. Most of the time, or probably all of the time, this is going to hold true. Constitutional isomers, resonance structures, they're going to have the same charge as the original molecule. So sometimes people will try to mess you up and try to ask you, oh, is this different from this molecule? Or like, what is this? Is this a constitutional isomer? Is this a resonance structure? Or is it the identical compound? The way that they sort of trick you with identical compounds is, okay, so I look like this here. I have, I don't know, a chlorine here. And then I say, now it looks like this. Is this a different molecule? Well, no. We can see that oh, let's say if I flip this guy around, it would be perfectly matched with this guy. So you don't really have to worry about, so if you see this question, sorry, my cat's distracted me. If you see this type of question, think about it as if you were flipping the molecule around, you're twisting around, you're doing everything you can to try and superimpose the molecule in question with the original molecule. So this is where the molecular formula kit, like the 3D model kit, comes in really handy, doing these types of, oh, is it a constitutional isomer? Is it the identical molecule? Or is it just a resonance structure? I hope I explained that all this stuff okay. I sort of rushed it, I'll be honest. But let me know if you have any additional questions. I'll see you next time.